All right, this is AP Chemistry section 3.3, and we're starting this idea of common ions. So the first part of this section talks about Le Chatelier's principle and how it relates to KSP. If you haven't done so yet, you need to go into your textbook and look at the two reading assignments that I gave you. Both of these have to do with equilibrium and Le Chatelier's principle. On the AP exam, a lot of equilibrium questions will say, justify your answer, and then they specify in terms of Le Chatelier's principle. And so you have to be able to take this and relate it to various situations. So go back and look at the textbook. So now that you've done the reading assignments for the last 2 days, I'm going to give you the simplified version that I use in my head. It just makes sense to me. Hopefully this will help you and not confuse you. So if you look up at the top, I have a reaction and I have the Kc expression. This is exactly as it's written on your AP formula sheet. So this is the reaction I'm going to use for this example, just so we have something to look at in terms of equilibrium expressions. So first we're going to look at a system that is at equilibrium. And the way I think of equilibrium, somewhat like a teeter-totter or a seesaw, whatever you want to call it. Something you'd see at the park where there's some sort of a fulcrum and then there's a large board and a kid sits on one side, a kid sits on the other. And if it's perfectly balanced, here it is, and it's just going to stay still. It's not going to tip one way or the other. As long as the kids are the same weight or they're at the right distance from the middle bar, it's going to stay balanced. And so this is my equilibrium. And at this park, and we're on this teeter-totter, once we get this balanced, we're setting a basketball right here above the center bar. And this basketball is going to show us where our equilibrium is moving as we put a stress on the system. So Le Chatelier's principle has to do with we're at equilibrium, we add some sort of a stress to the equilibrium, and then we find a new equilibrium. So here we have adding product. So adding product will increase the value of Q, because if you look back at your equilibrium expression, the products are on top. If you increase the numbers on the top of the expression, the overall value gets larger. And so adding product will increase the value for Q. Now here's what I normally do on paper. I set Q and K on a number line, and you don't have to have numbers. You just have to know which one's bigger. So here's 0, here's K. We increase the numbers on top of the expression, and that led to Q. Q is greater than K. So on a number line, the way I think of it is that Q is always trying to be K. And so wherever K is, that's where Q wants to be. So if Q is here, it's greater, it is going to move to the left. And by move to the left, here's what I'm talking about. So look at the expression up here. So we added some product. When I say shift left, I'm talking about favoring the reactants in the expression as written. That's what a shift left means when we use it in this context. So let's look at my teeter-totter. So we're adding products. We added some products, and I don't know, let's just say that we're, stacking things under this. The more you stack under it, it lifts this side. And what happens to the basketball? That shows us which way we're going to shift. So if we add the number of products and we lift this side, the ball is going to roll to the left, which is a favoring of the reactants. if we add reactant to a reaction when we're at equilibrium, it would decrease the K. So if you look back up at your equilibrium expression, if you increase the numbers on the bottom, then the total number is going to decrease. When you divide by a bigger number, the answer gets smaller. So we add the reactant, that decreases Q. So when we put this on the number line, here's 0, here's Q, and it has decreased from where it was in equilibrium. So it's smaller than K. And Q, always trying to be K, is trying to be where K is, shifts right. Looking back up at the top of this reaction, adding product, we're adding reactant, and that causes a shift to the right. It favors the products. So let's look at our teeter-totter here. So we're adding reactant. So imagine that we are stacking things under this end and it's lifting it up. We have increased the number of reactants. And which way is this basketball going to roll? It's not going to stay in the middle anymore. It's going to roll to the right, favoring the products. So this is my very simplified version of Le Chatelier's principle. So now let's get into the actual notes for section 3.3. Looking at example 1, consider the dissolution of calcium hydroxide. And we're given a chemical equation and a KSP. It says calculate the molar solubility of calcium hydroxide when the salt is placed in pure water. So let's go ahead and make a chart, ice chart. So we've got initial, change, and equilibrium. So initially, we're talking about pure water. We have no calcium ions in the water. We have no hydroxide ions, and calcium hydroxide is a solid, and we know that solid S stay out. It's going to stay out of our equilibrium expression. It's not going to factor into any of our calculations. So then the change. So we are adding our solid to pure water, so we know we're going to get some products. So the change is going to be positive because we're going from 0 to something other than 0, something greater than 0 in terms of products. And it goes up by a certain amount. Now the coefficient for calcium is 1. And so what we have is 1 times S, or just plus S. For hydroxide, we have 2 as our coefficient, so it's plus 2 times S. And remember, S is that molar solubility. So far, everything we're doing here is review from previous section. So at equilibrium, we have S for calcium, we have 2S for hydroxide. We can figure out the value of S by using the equilibrium expression. So Kc, the equilibrium expression for this reaction, is concentration of calcium ions. And that's to the first power because our coefficient is 1. Times the hydroxide concentration to the second power because its coefficient is 2. We can plug in all the numbers that we know. We know a KSP, I should have written KSP here. We know KSP, it is 1.3 times 10 to the minus 6th, no units. And we know that calcium is S, and we know that hydroxide is 2S, and we have to square this quantity. And so we end up with, let's see, that's actually 4S cubed. So when we solve for S, we come up with 6.9 times 10 to the minus third molar. S, the molar solubility, has units. It's molar, moles per liter. And so that's what we did. We calculated the molar solubility. That's this one, that's S. If you wanted to calculate the concentration of calcium at equilibrium, it's the same as S. If you wanted the concentration of hydroxide at equilibrium, it would be 2 times S. In this same question, it says, is this solution acidic or basic? AP level acid base is later in the year, but all of you have had Chem 1, and we know that in an acidic solution you have more H plus than OH minus. In a basic solution you have more hydroxide than hydrogen ions. And so we have a source of hydroxide ions. We don't have a source of hydrogen ions. So there's going to be more hydroxide ions now, and that makes the solution basic. In the next part of the example, it says, suppose some acid were added to the saturated solution of calcium hydroxide. Write the equation of the second reaction that would take place. So if we're adding an acid, we are adding H plus. And we have a solution that already contains hydroxide. And when these two ions react, we end up with H2O, liquid water. So the question now is, would the solubility of calcium hydroxide increase or decrease? Explain the change in solubility using Le Chatelier's principle. So let's think about this. We are adding this hydrogen to the solution, which is decreasing the concentration of hydroxide. When we go back and look at the original equation, what happens if we decrease the concentration of hydroxide? Think about it in terms over here. Now, it doesn't fit these exactly because here we are getting rid of some rather than adding. So let's take a look at how this would work. Here's my original equation. Calcium hydroxide So here is my teeter-totter at equilibrium. And here's the basketball sitting in the middle over the bar. So what we are doing is decreasing the hydroxide. So let's think about it. Maybe we've got some supports here that are holding things up. What happens if you start taking these away? So if you are decreasing a product, that side starts to go down. And now where's the ball going to go? The ball was here in the middle. The ball is going to start rolling to the right. So we are talking about a shift to the right, which means this. You could say it favors the products, or in this specific instance, here's what happened. Solubility increases. Adding acid removes hydroxide from solution. So the reaction will shift right. So this is what happens. Next point, notice that the dissolved ion hydroxide reacts with the added H plus in a side reaction. In general, when there's a substance that reacts with a dissolved ion, the solubility of the salt increases or decreases. In general, if you have a second reaction that reacts with one of the dissolved ions, the solubility of the original solid will increase. Suppose calcium hydroxide were placed in a basic solution. Would the solubility of calcium hydroxide increase or decrease? Explain the change in solubility using Le Chatelier's principle. All right, so using this same idea, placing it in a basic solution. So if you place it in a basic solution, we're going to have an increase in the amount of hydroxide. We don't need it. So in a basic solution, we are increasing the hydroxide. You're increasing a product. So in terms of Q gets larger, and then we could predict there's going to be a left shift. If we were talking about it in terms of our teeter-totter, when the products are increased, we're talking about that side tipping up. Where does the basketball go? It rolls to the left. Both of these things tell us that in terms of Le Chatelier's principle, increasing the hydroxide will decrease the solubility of this particular salt. Solubility decreases. Adding base will increase the hydroxide in the solution. So the reaction shifts left. Forming solid, or we would say forming more precipitate. Notice that when an ion of the salt is already present in a solution, that would be this hydroxide, the solubility of the salt decreases. Adding a common ion decreases concentration, decreases solubility. In a solubility equilibrium problem, the equilibrium can be affected by adding or removing ions in the solution. This will affect the solubility of the compound. If a solution has the same ion as one of the ions in the dissolving compound, we call that a common ion, and the effect that it has on the solubility of the compound is called the common ion effect.